Okay, we're going to pick up where we left off when I had the technical difficulties. What we were doing was we were checking, still working on our assumption of normality. We checked skewness and kurtosis values, and we compared them with the standard set by Huck. Now, the additional piece to checking skewness and kurtosis values according to Huck is we can check the skewness and kurtosis values for significance. And in this case, we would not want our result to be statistically significant, because this test of significance is saying, is it statistically significantly different from normal? All right, so we want the answer to be no, and so we don't want significance in this case. All right, the way it works is you take your, let me get my pen to working. Let's see if it cooperates this time. There it is. Okay, so you take your skewness value. So we have negative 0.422, and we're going to divide by our standard error of skewness. So that is 0.241. The answer we get is 1.75. All right, so we've essentially standardized our skewness value is what's happening. Because we have it standardized, we can put it on our normal distribution. So if you look here, I've marked this 1.96. So you can kind of think of this as, let me get my pen to work. Again, I'm not having good luck with my pen today. But you can kind of think of the 1.96. This is your, this is Z. These are standardized. And remember, for every Z value, we have a corresponding probability, right? So the probability for 1.96 is 0.05. And remember, this is our critical value, right? Our P critical. So what we're going to do now, when we check for normality by doing this dividing, we can't get a probability, but we can get a Z value. So we're going to compare our obtained Z value to this critical point. And we don't want our obtained value to exceed our critical point. So our critical point is going to stay the same. We're always going to compare to 1.96. And if our obtained value is out here somewhere, then we know that we do have statistical significance, which in this case would be bad, right? Because we don't want it to be significantly different from normal. All right, but I can see that when I make this comparison, it is less than 1.96. So yay, it is not significant, which would indicate a normal distribution as far as skewness goes. All right, so let's flip back over and do the same thing for our kurtosis. Okay, so we are going to take negative 0.179 and divide by 0.478. And let's see what that's going to be. It's going to be a decimal something, right? It is 0.374. All right, so 0.374. If I go back to my graph here, if I know that 0, one day I'm going to have a computer that's better for this. All right, if I know that 0 is right here in the middle, the 0.374 is going to be what right here? Really close to 0, right? Well, it's still not larger than 1.96. So neither of these skewness or kurtosis values are significant. So yay, that's an indication that we do have normally distributed data. All right, so I'll put that in a little sentence down here to help us remember what to do. So in this case, we're going to divide skewness by the standard error of the skewness and compare to 1.96. We want the value to be smaller than 1.96. If it is, our data is normally distributed. And then, we do the same for kurtosis. Okay? So let me go back to my PowerPoint and look Now remember, I'm checking multiple ways, but like I said, you find one you like and you go with it. So I've done the PP plot, the QQ plot, I've checked skewness and kurtosis values for significance. I've compared skewness and kurtosis values to what Huck said in 2004. The last option I have here is the KS test. And the KS test really is not performed very often as far as our students go anyway. So let me go to Analyze, Descriptives, and I believe it's under Explore. Let me check. No, I always forget where this one is because, oh, there it is. Okay, let me back up. All right, so Analyze, Explore. I clicked over the variable I care about, and it's here under Options. I always think it's under one of these two, but it's under Options. I said it wrong. It's under Plots. Obviously, I can't remember where it is. I don't use this one very much, if you can't tell. All right, now I'm going to check this button, Normality Plots with Tests. So this is going to give me a test, the KS test, and I'll show you why they abbreviated KS test here in a second. So when I say OK, there it comes. I'm going to scroll down here. There it is. Okay, test of normality. At least it's labeled nicely. All right, here's the KS test. So I'm not going to butcher this name and try to say it, but this is a test again against normality, and we don't want significance. Right? So we're good. We're good to go here. 0.200 is not statistically significant. All right. Now, how did I come to that conclusion that it's not statistically significant? When I'm evaluating that SIG column or that probability column, that's what this is. This is probability, remember? And when I'm evaluating whether or not that value that SPSS gave me in the table is statistically significant, what am I comparing it against? Do you remember? 0.05, that's our critical value, that's our cutoff value, that's our alpha level, whatever you want to call it. We're comparing our obtained probability with our threshold or our cutoff point, which is 0.05. Well, 0.2 is bigger than 0.05, which is good for this because I don't want it to be statistically significantly different from normal. All right, so good news is the two skewness and kurtosis methods and the KS test all indicated our data is normally distributed. We can probably be pretty confident then that it is normally distributed. If you want to take a look at your data and see, did it give me a histogram down here? I don't think so, no. But you could ask it for a histogram if you want to see one. You can get it under Chart Builder. And histogram, we just want a simple histogram. And if I want to put percentage of lectures here, I can say OK. And you can visually take a look at it. Okay, so that's our histogram. Does that make a perfectly normal, beautiful bell curve? No. For one thing, we're capped out at 100, right? You can't go over 100% of the lectures. And so we have a little bit of a bump up here. Looks like some people didn't come to class very often, but it's relatively normal. So it goes along, this visual histogram goes along with what all our assumption checks indicated. All right, now let's look at our last assumption, which is homogeneity of variance. And we are going to check this when we run the ANOVA. So this one is a little bit weird. The rule is, or good practice says, you check your assumptions before you run the analysis, right? That's what I've been telling you. Do these things before you run the analysis. But here's the weird thing. This assumption is actually checked when you run the analysis. All right, so it's a little bit backwards. What you'll want to do is check all the assumptions you can, and then just kind of hold on to this one until you run the analysis, and then you can check it, and I'll show you how to do that pretty quickly in the output that SPSS gives you. But before we do that, I want to just draw you a little visual about what this assumption is describing. So this is homogeneity of variance. And I said before that we know that homogeneous means the same. So we're checking to see, are our variances of our groups or our levels, so in the independent variable, which for us, in our case, these are the universities, all right? Our independent variable has 2 levels because we have 2 groups, all right? And as we get into the more advanced forms of ANOVA, we're going to talk about this more, but that's what that means. The independent variable has 2 levels. So the variance of the outcome variable, which is % lectures attended, should be consistent at all levels of the independent variable. Okay, so if I'm thinking about my Duntstown and my Sussex, so I'm going to put an S and a D, if I plot their % of lectures attended, I want that curve to be relatively homogeneous, right? Because this is homogeneous of variance. So this spread outness needs to be relatively the same. Now, it doesn't mean the mean has to be the same. This mean could be 50%, and this mean could be 80%, or vice versa, or anything else. So it doesn't mean the means have to be the same, but it does require the variances be this relatively equal, not the same, but it needs to be relatively equal. So the spread outness needs to be relatively equal. So let's think about why that's important. If the mean is supposed to be the number one value that best represents the distribution, was that a flashback from last semester? Yes. All right. So the mean should be the number one value that best represents everybody in the distribution, and the same here. Well, what if you have a situation where you end up with, say, this in Sussex? Maybe their average is like 20%. Maybe they're such smarty pants they didn't really think they needed to come to class. And what about the Duntstown people? What if their variance looked like this, where they're really platykurtic? Maybe they still had an attendance average of 50%, but it was really spread out among the students. All right. So when analysis of variance, when we're comparing the means of the 20 and the 50, what we're looking at is a couple of situations where the mean is not really representing everybody very well or very equally. Here now this is doing a better job than this, but because our variances are not relatively equal, ANOVA doesn't feel like, the test doesn't feel anything, does it? But ANOVA doesn't work properly because the variances are not similar enough. Okay, so this situation right here, this would be an example of a failure of homogeneity. Whereas this up here, even though the means are different, that's okay. This would be a pass of the assumption. We would meet the assumption because the variances are relatively equal. Now, I just totally made that up, and I'm eyeballing it, but you can get an idea. And then down here, our variances are really different. So this would be a failure. Now, we don't evaluate it with pictures. We evaluate it with this Levene's test. So if you get really proficient at statistics and you invent a test or invent a statistic, they'll name it after you. So we want the result to be non-significant, because a significant result, again, would mean that these are different. And we don't want them to be statistically significantly different, right? We want them to be the same. So we'd want a non-significant result. So when we find Levene's test in our output, we're going to have that sig column, right? And we're going to take whatever's there and we're going to compare it to our standard, which is 0.05. And we want it to be greater than, right? That's a question mark right there. Whatever this is, when we compare it to 0.05, we want it to be greater than, because we don't want significance. Okay? We want a situation like this where they're not statistically significantly different. All right? Now, that's a long discussion of assumptions. When we start checking them, it won't take nearly that much time. But when we first start going through them, it does take a little bit of time. All right? But that concludes our practice for assumptions. I'm going to move on to a discussion of the ANOVA and incorporate checking the assumptions along with making sure we hit all of those write-up pieces in the rubric.